Hello everyone, welcome back to my class, and today we will talk about Young's double slit experiment. Yeah, we are in module 4 and we have already discussed interference of light waves and the role of polarization in observing interference fringes is also discussed, and let us start today the Young's double slit experiment. But before moving ahead, let us talk a bit about interferometric devices which people usually use in the labs. And to observe interference, we use different devices like Young's used two slits. Okay. We in the last two lectures we used 2-point sources, okay, and they form they are the part of some experiment, and therefore, it is called interferometric devices, a device which let us observe a particular type of fringe pattern. Now, these interferometric devices can be categorized in two separate categories. Okay. Now, why we are separating them in two categories? Because their working principle is slightly different. Okay. Now, this interferometric devices, one set of these interferometric devices work on wavefront splitting, okay, and the second set work on amplitude splitting. Okay. The first set produces interference by splitting the wavefront and then again letting them superimpose, okay, while the second set splits the amplitudes of the incoming wave, and these splitted amplitude are then let to overlap. Yeah, these are later made to overlap in space, and thereafter they produce interference fringes. Okay. Now, what are wavefront splitting? A beam is allowed to fall on two closely spaced holes, and the two beams emanating from the holes interfere. This is how wavefront splitting interferometric devices are defined. Okay. Now, the best example of this kind of interferometric devices is our Young's experiment. Okay, this is the best example for this type of interferometric devices. Now, amplitude splitting. In amplitude splitting, a beam is divided at two or more reflecting surfaces, and the reflected beams interfere. Now, the best example here is our soap film or thin films. Suppose we have a thin glass film and then a light falls on this film, a part get reflected, a part get transmitted. The transmitted part again get reflected back, and then it comes out, and then it interfere with the initially reflected wave. Okay. This is the other way of observing interference, and such kind of such devices which produces this type of interference is called amplitude splitting device. Now, here you see amplitude A is falling from top, a portion of this amplitude is, say, A prime is getting reflected, and the rest A double prime is transmitted, and this A double prime again a part get reflected and again get transmitted, and therefore, the interference is happening between two different amplitudes of the same incoming wave. Okay. While in Young's double slit experiment, we launch a wave, okay, and traditionally it is a spherical wavefront, and then these openings at these holes, they allow only a part of the wavefront. It means the wavefront is getting splitted here in this device, and therefore, this is called wavefront splitting interferometer. Okay. Now, once we have defined these two terminologies, let us move ahead to our Young's double slit experiment, which is of course, a wavefront splitting interferometer. Now, Young's, we know that the interference requires coherent wave. Okay, once we have a coherent wave, then we would be able to produce very nice and beautiful fringes. But at the time of Young's, lasers were not invented. Okay, and since the lasers were not available there, then people were not knowing how to perform these experiments with a incoherent source. What Young's did is that he took a very small pinhole, okay, and put it in front of sun, okay, and if the hole dimension is very small, then the light which is coming out of this hole would be spatially coherent, okay, and if it spread a lot, then it will cover a larger region. What Young's did is that he put another screen with two holes, S1 and S2, again a very small, and the spread in the wave which is emanating from source S or hole S is such that it covers the two slits S1 and S2. Under this criteria conditions, the Young was able to get a very nice coherent, spatially coherent light, and when these waves are interfered, on the screen he observed very nice beautiful fringe pattern. Okay. Now, let us do a bit of mathematics and let us try to find out the condition of interference, the position of maxima and minima, the fringe width. Okay. Now, this was the first plane in which a small hole was made, and this hole, small hole, works as a source S. Now, next to this first plane, a second screen was kept with the two holes which are named as S1 and S2, and these two holes are separated by a distance A. This is the schematic picture of Young's experiment here. The light coming from source S falls on slit S1 and S2, and from here they propagate in a right direction and then they overlap in space. Okay. The screen is placed at a distance d from S1 S2 screen. Now, the point of observation is at observation plane. Now, suppose the distance between source S1 and P is R1, while the distance between source S2 is S2 and P is R2. Okay. Now, if we want to calculate the path difference of wave which are interfering at point P and starting from source S1 and S2 respectively, then what we will have to do is that we will have to draw a perpendicular from S2 on S1P, okay, and this S2B is the perpendicular. Okay. Now, the path difference would be S1B. Now, since S1B is the path difference, then this would be equal to R1 minus R2 under the approximation that P is very close to O, okay, and S1 S2 is also very close. Okay. The two approximations which we assume here in this experiment is that S1 S2 is very close, that is A is very small, and capital D, which is the separation between the source plane and the screen, is very large. Okay. Under these approximation, the angles which are subtended by the S1P and S2P, this can be assumed to be equal, and for simplicity we assume it to be equal to theta m. M stands for mth fringe. Here we are assuming that mth fringe is being formed at the point of observation P, which is at a distance y m from the center O, center of the screen. Okay. Now, if we look into the triangle S1 S2B, this triangle, then R1 minus R2, which is S1B, would be equal to A sin theta. This is your theta. Here theta is theta m here, M stands for mth fringe, as I already told you. M stands for mth fringe, and if we do not want to talk about the, or if we do not want to take into account the fringe number right now, then we can assume that theta m is equal to theta. Yeah. Now, S1b from this figure, since S1 S2 is A and this angle is theta or theta m, then under the approximation that capital D is very large and small a is very small, A sin theta would be equal to A theta, because sin theta would be equal to theta. Okay. Now, let us calculate tan theta. Tan theta would be equal to y m by d. Yeah, because tan theta is equal to again theta, because theta is very small, y theta is very small because the screen is placed at a very large distance from the source plane. Okay. Now, what does theta represent? Theta represents the angular position of a fringe, mth fringe, which is at a distance y m from point O. Okay. And capital D is the separation between source plane and observation plane. Now, therefore, once R1 R2 is given as A theta and theta is y m by d, then we can substitute the expression of theta from here to here, then this gives R1 and R1 minus R2 almost equal to A y m by d. Okay. And what is R1 minus R2? R1 minus R2 is optical path length difference. Okay. Now, let us implement the conditions of maxima and minima. For constructive interference, constructive means for maxima R1 minus R2, the optical path length difference must be integral multiple of lambda. Okay. We have already talked about it. Now, let us substitute R1 minus R2 is equal to m lambda and see what happens here. Here we are substituting it here in equation number 25, and from here we get y m is almost equal to d, capital D by small a, m into lambda. And what is y m? Y m is the position of mth fringe from the center of observation plane. Okay. Once we have this position, then we can calculate the angular position of maxima. Yeah, we have two sources which are in a plane or along a line, and here we have a point of observation P. Once we know this distance, which is y m, which is given by equation number 27, then we can also calculate the angular position of mth fringe. Okay. How to calculate angular position? Because we know angle is equal to arc by radius, or you can also exercise the tan theta formula. Okay. And from there, this angle theta m would be y m by what is radius? It is d. And what is y m? Y m from equation number 27, it is d by a m lambda by d, and d will go away, we are left with m lambda by a, and this is what written here in equation number 28. Okay. This gives us the angular position of the mth maxima or mth bright fringe. Yeah, m stand for m is integer, which stand for the counting the number of bright fringe. Okay, and the fringes are being counted from the center on the screen. Here the point O is sitting here, the 0th fringe is here, all positive fringes are above O, all negative fringes are below O. Okay. We can also treat the fringes below O as positive fringes and fringes above O are negative fringes. It is entirely up to us. Now, once the fringe positions are known, let us calculate the fringe width or spacing between the fringes. How to calculate this? We know the expression for mth fringe, and therefore, we also know the position of m plus 1th fringe. Let us take the difference, and this will give us the width of the fringe or fringe spacing. Okay. We subtracted y m from y m plus 1, and this will give delta y, which is fringe width, which is equal to capital D by small a into lambda. Okay. This fringe width is function of wavelength. Okay. Larger the wavelength, larger would be the fringe width, and this is why red fringes are broader than the blue ones. Okay. Now, we know that for two overlapping spherical waves, the phase difference is given by this relation. This we have already seen when the spherical wavefronts were met to overlap, and then we calculated the phase difference in the case where the initial phase difference was 0. Yeah, this is the phase which is equal to k r1 minus r2. The same can be exercised here also. Now, we will substitute this phase expression into equation number 13, which we derived earlier, and this will give us the irradiance formula, the expression for irradiance, which is 4 I naught cos square k r1 minus r2 by 2. Okay. If you do not remember what was there in equation number 13, then I would for you I can write it here. It was this expression. This was the equation number 13, and here we substituted for del. Okay. And this gives equation number 31. Okay. Now, in equation 31, we know what is the value of r1 minus r2. We calculated it here. In equation number 25, we calculated the value of r1 minus r2. We will substitute it back, and this gives the expression of irradiance, which we will observe at the screen in Young's double slit experiment. Okay. Now, we can plot I as a function of y, the position, then at the center we get a maxima, and then at this value of y we get minimum, and then again at this value of y we get next maximum, at this value of y next minimum, next maximum, and similarly for the corresponding negative values we get maxima and minima alternatively on both sides of the central maximum. Okay. This is our central maximum, and these are the different orders. Okay. M1 m is equal to plus is on right hand side, plus m, and minus m are here. Okay. Now, we see that the fringe widths are same. Yeah, the peak to peak separation or deep to deep separation is the same. Okay. And we assume that each slit was infinitesimally wide, which means that each slit is considered to be of 0 thickness. Okay. We have a point source, and we kept point source along a line, and this point source created a one dimensional object which has a length, but no width, and therefore, it has infinitesimally wide width. Okay. And this infinitesimal width therefore lead to cosine fringes or periodic variation in the intensity. Okay. And this the periodicity is ideal, yeah? There is no change. Okay. But in actual case, we cannot form a slit with 0 width. In reality, in real life, all the slits will have certain width, and if you take the width into account, then the intensity of these peaks, which remains constant, will drop down. Okay. Once the finiteness of once we consider non-zero width of slit in Young's double slit experiment, the intensity will slowly drop down, and the resultant fringe pattern will now look like this. This is the central maxima, and for guidance I am drawing this dotted line. The next maxima would be a bit smaller, the next a bit smaller, the next more. Yeah, this is how the intensity will go down. Yeah, this is due to diffraction. Okay. The actual pattern drops off with the distance on either side of O. This is O. Yeah, and this is because of diffraction. This is because of the width of the slit. Okay. Now, this is all in Young's double slit experiment. Now, let us again go to next arrangement, and this is another type of interferometric setup, which is called Lloyds mirror. Okay. In this case, we have a mirror, this is this dark line represents a mirror, okay, and a light from source S1 falls on this mirror, okay, and then it get reflected here, okay, and this reflected light interfere with the direct light which is coming from the source. Okay. We know that the source S1 is a point source, therefore, it would emit spherical wavefront. Now, let us draw this spherical wavefront. Now, here at the mirror what will happen? This sphere now collide with the mirror and the part of this sphere will now get reflected and it will generate a reflected spherical wavefront. This reflected spherical wavefront will interfere with the directly incident spherical wavefront. Okay. This arrangement can be understood by assuming a virtual image of S1 as S2. The light is falling on the mirror and then it is getting reflected. If we trace these lines back, then they joins at point S2, which we assume as virtual image of S1, or S2 can be treated as virtual source and the separation between S1 and S2 is A. Okay. Since the interference here is happening between direct light and the reflected light, this interference is slightly different from what we observe in Young's double slit experiment. Okay. What is the difference here? After reflection, there is a phase shift which the reflected light will bear. Okay. The light which is falling on the mirror, after getting reflected, it will carry an additional phase of pi. The reflected light will get shifted by a phase of pi, and due to this additional phase, the conditions of maxima and minima will alter. They would actually be exchanged. The integral multiple of wavelength will lead to dark fringes. Okay. Therefore, contrary to Young's double slit fringe pattern, the dark here would be treated as bright, or at the position of dark fringe we will get bright fringe, while at the position of bright fringe we will get dark fringe. Okay. And therefore, the condition S2p minus S1p, which is equal to integral multiple of lambda, this is condition of minima. Okay. Similarly, this condition is for maxima, and therefore, this experimental arrangement produces a fringe pattern which is complementary to that of Young's interferometer. Okay. This is all for today, and thank you for hearing me.